about iterables and iterators. This is a beginners slash fundamentals talk. Python has this powerful and clean abstraction for iterating or looping through collections called iterators. We're going to take a look at how iterators are implemented within Python, and then also lead up to we're going to lead up to creating our own iterator. So when we start programming, we often learn iteration this way. We take an array of elements. We see, we use what we know. We take, you say, okay, well, let's get the total count using length. And we initialize I to 0. And we use the while loop where we take, we go through and loop through I, assigning the I to cities, pulling out each city, and then printing the city and then incrementing I. When we then we eventually find out that, oh, well, there's a range function. Well, the range allows me to get a list of integers from 0 through the length of the cities. So let me use that, and we go through and we still use I to pull out the city and print each city. But this is still the wrong way to go about thinking about this. The right way is to say, okay, well, cities is this stream of values. I just want to pull out each city and print each city. And this is what iterators allow us to do. So what is an iterable? Well, an iterable is an object that implements the dunder method, iter. It's expected to return the iterator. Now, within Python, there are a lot of different constructs and collections that give us that are iterable. There's list, dictionaries, files. So let's take an example. We take cities again. We run the dir method on cities, and we get a list of dunder methods, iter being one of them. And so we see that cities is actually an iterable. Well, what's an iterator? Well, iterator is an object that implements the next dunder method. It's expected to return the next element all the way until there are no more elements available. And then when there are no more elements available anymore, it raises a stop iteration exception. Well, let's take cities again. Let's invoke iter on that. We get the iterator and invoke the dir method. And we see that there is a next dunder method there. So that's our iterator. So this is the generalized loop for iterators. The for loop is a very powerful construct within Python. And the iterator produces a stream of values from the iterable. We assign name to that stream of values and execute a group of statements for each element returned. There are many things within Python that are iterable. We've already seen that lists are iterable. Here we take, Sacramento, Phoenix, Salem, etc. We assign that stream to name and print out each element. Well, strings are also iterable. Here we get a stream of characters back and print out each character. Dictionaries are another collection type that is iterable. Here we have states, which is a combination of pairs of state versus capitals, I believe. we get a stream of elements back, and what we see here is what we print out. What we get back is a stream of keys. Counterintuitively, I would have expected us to get back keys and value pairs because that's what we most often use. But fear not. Dictionaries have methods on them that allow us to get back values and also items as well. And these also are stream of values of key value pairs, for example, and we can print out the key value pairs. Now, going back one slide, one thing that you might notice here is the values returned from the stream is in order of insertion. And this has only been the case since Python 3.7. Before that, what we used to get back from the stream, or from the iterator rather, is it was in random order. Tuples are iterable as well. Now, collections are not the only things that are iterable. Here we see that we can take a file and loop through. From the file we get a stream of lines, and we can process each of these lines. This is really powerful within Python. Scander is another function that takes in the path, returns a stream of file objects. We can print out those file objects as well. Using the regular expression library within Python, we get a pattern object back, and then we can execute the findIter method on the pattern, returning a stream of matches, and we can print out each match. Now, within Python, there's a really cool package called Iterators. The first two methods here, count and cycle, are really interesting because they return iterators that never end. A count gives us back a stream of elements from 10 onwards to infinity, and cycle loops through A, B, C, D, and F over and over again. Now, one thing that's two things really that this illustrates is iterators do not need to ever end. And the second is iterators don't actually store the values that they're going to return. They evaluate them at runtime. They only store the current value at which they are at, and then the next time next is invoked, it evaluates and gets back the next element. Some more methods within itertools are accumulate and chain. Accumulate returns an accumulated sum of members from within the stream that's passed to it. What's interesting here is it's actually maintaining state of the accumulated sums, till that member that it is actually at. Chain loops through each iterable till it gets to the end, and then to the next and the next, and so on and so forth. So we see here that it's possible to do some really powerful and complicated logic within these iterators. List comprehensions are a way of creating lists by invoking a function on each element within the stream. It then returns another iterable. Sum, min, and max are interesting because they take iterables and return the sum, min, and max of the list, or the list of numbers that are passed to it.
Could I ask a?
Sure.
Do you mind if I interrupt for a quick question?
Go for it.
how would you exit a loop, such as for I in cycle, quote, A, B, C, D, E, F?
Yeah. So you mean in the case of like cycle? Yeah.
Yeah.
You could break out of that. Or you can create a condition through which you can evaluate that and then break out of that. Yeah.
How would I break out of that?
Oh well, let's say that you perhaps you're counting the number of times you have cycled through A, B, C, and D, and F, or some, or the number of times A has appeared, for example, and then you can break out of that. Yeah.
Would you raise an iterator, or would you raise an exception? How would you normally break out of that?
You could actually, that's a good idea, actually. You could actually raise a stop iteration function, a stop iteration exception.
Cool, thanks.
Yeah. Yeah, so going back to sum and min and max, the reason I have them here is because we see that the for loop is not, for loop here is actually implied. Now, sometimes it's possible that we may actually want to get the index out of along with the member of the element that we're returning out of the stream. Well, we can use, instead, we don't go back to using the naive approach that we used before. Instead, we use an enumeration. An enumeration can take an iterator and return both the index and the object. Now, this is really powerful because enumerators only take iterators as a parameter. So we can take something like a file and actually print out line numbers from the file for each line. Here we have a zip function that takes a pair of streams and gives back a stream of pairs. We pass in two iterables into the function and manipulate them into yet another iterable. This illustrates how powerful iterators are within Python. Now we're going to take a look at how we can customize iterators. Let's say we have this sentence. We want to print out all the words that have even number of characters within this sentence. So we, execute the split function. We get a stream of words back. We go through and we evaluate each word, and take the length of each word and see if it contains an even number of characters, and then we print out the length and the word. Well, one thing to notice here is we're actually doing two things within this loop. One is picking out the word that we want to actually print, and then printing the word. Instead, what we can use is a generator. A generator is a function that returns a stream of characters, rather a stream of values. And what do we know that actually takes a stream of values and allows us to loop over them? Iterators. And finally, we come to, I promised that we're going to create an iterator, and that's what we're going to do. Here we have a myRange class that takes a start and an end. We assign start to the value and end to the end element member. We see that we have an iter method, the dunder method, that returns self. So we know that this is an iterable. We also we also implement the next dunder method, which returns the current value, and then every time it gets invoked, increments the value till we get to end, and then when we get to end, it raises the stop iteration exception. that's all, folks. There's a GitHub link here for the presentation and the code. I've added my details here. Love to chat about. Please do connect. I'd love to chat about languages, cloud services, and big data computing. Yeah. Any questions? Any other questions, rather? Yeah.
So hello, everyone. Thanks for having me. So the talk today is on Ray, which is a system for scalable Python and machine learning. So a little about me. I currently work in developer relations at Anyscale. So what that primarily means is what you might expect. At least in my case, a lot of it is writing about distributed computing, editing a lot of blogs, going to events, listening to events, and working with the Ray community in general. So previous to that, though, I worked as a data scientist at Scripps Research. So a lot of that was actually working on wearable devices like Fitbits and similar, looking at longitudinal trends between heart rate, sleep, and activity. It was really cool seeing, inverse relationships between activity and, heart rate. So during Christmas, activity, went down and heart rate went up. So it was a lot of fun. Interesting in a lot of ways too. So I also teach class at Stanford Continuing Studies. So I teach machine learning with Python, I do some LinkedIn learning stuff, and so on. So now onto the meat of the talk. And before we actually get into what Ray is, it's important to really take a step back and, so take a step back and really discuss why we need distributed computing, and at least from a machine learning perspective. So the plot on the screen is from OpenAI, and it shows the compute demands to train state-of-the-art models between 2012 roughly and 2020. And you have a pretty massive growth rate here, roughly 35x every 18 months. It's really important to note that this graph's on log scale. What we have here is Moore's Law, and Moore's Law has really powered the tech industry for decades. Processing performance has doubled every 18 months, and while 2x is impressive, it's really not 35x. Moore's Law is also likely, sorry.
I'm saying is I didn't see the slides advancing. Is anyone else seeing it? I just see the About Me slide.
Oh, sorry. Let me.
That's all right. I thought you'd want to know.
Yeah. Let me go back. You see now?
No. I see the About Me slide.
Okay, let me close the presentation. Okay, so if you'll see the first slide, if you'll see the second one.
Yes.
I see About Me, I see it advancing, and now I see this. Now I see what you're talking about.
Wonderful.
That looks more like log scale.
Yeah.
Cool.
So before we get to what Ray is, and so we have this graph here, I just mentioned it. So we have a 35x increase every 18 months, and this is in log scale. So we have now is what I was talking about before is Moore's Law. And Moore's Law is part of the tech industry for decades, of course. And while 2x is great, it's certainly not 35x. And even Gordon Moore lately has been like, it's not continuing forever. What we have on the far right of the screen is GPT-3. And that model has 175 billion parameters. And it's currently, at least last time I checked, the largest model released by OpenAI. And it's getting pretty clear that compute demands and memory requirements are rapidly increasing. So let's now look at like specialized hardware like GPUs and TPUs. And while the performance of GPUs and TPUs have really brought a lot more computational power to the table, they really only help to prolong Moore's Law further in the future and not really fundamentally increase the rate of improvement. So in other words, they're not matching increased demand on their own. And to support these workloads, it would really help to distribute machine learning applications. The problem is kind of as follows, is that distributed computing has traditionally not been very easy. So now onto Ray. And so Ray is an open source project that began its life in AmpLab, RiseLab, and Bear at UC Berkeley. And these labs,
just to be sure, compute demands 2012 to 2020 is still the slide I see. Has it advanced since then?
Oh, it has. Oh no.
Sorry.
We're having this fun sort of thing.
Sorry about that.
Okay. If it has a issue, I'll go off presenter mode or
okay, no worries.
See if there's something we can do to to make this a bit easier for everyone. So what you have here in the graph is now you can see the GPU and TPU.
Yes.
So the TPU and GPU are helping things, but they're not really making life, perfectly better in a lot of ways. So of course we have Ray, and it began in UC Berkeley. So all these labs have experience developing Apache Spark, Caffe, Mesos, and of course Ray. And as far as what Ray is, it's supposed to be a simple library for distributed computing. So it lets you scale your Python applications to from your laptop to a cluster without really modifying your applications much. You just need to add a couple decorators, and more on that in a little bit. Second, at least for me, it's an ecosystem of libraries built on lower level primitives for scaling machine learning and more. So what this means is, since machine learning today requires a lot of distributed computing, and this makes it a lot easier because there's a lot of libraries for machine learning built on top of Ray. And finally, it's a collection of tools for launching clusters on any cloud provider, Kubernetes, or really anywhere. The idea is that the Ray API should be easy to write distributed programs, but it also should be actually easy to run them. And you really don't need to understand a ton about cluster management to run your workloads. So here's a depiction of the Ray ecosystem. So at the lowest level, we have the core Ray API, and that's an API for taking your Python functions, Python classes, and then distributing those to the distributed setting. So it's really general, and that generality is really important because you can build arbitrary applications on top of Ray. So on top of Ray, we have higher level native libraries as well as third-party libraries. For the native libraries, we have libraries like RayTune, which is a library for hyperparameter tuning at any scale. We have RLib, which is a library for reinforcement learning. And that's really important for reinforcement learning, as a lot of reinforcement learning applications are very compute heavy, and they're not traditionally the easiest to program. So more questions? Okay.
Yeah, one just came in.
Yeah, okay. So
what are some applications other than machine learning that can be built on Ray?
So a lot of it these days is going toward data processing, which I know that's not necessarily divergent from machine learning. But there's a lot of other things people are doing with Ray, but primarily how Ray started is machine learning, and now people are coming up with other applications for it. So we see in the image of the diagram, for like third-party libraries, people do build integrations with Ray. So like there's Dask on Ray, there's Modin, which is like parallel and distributed pandas, and there's integrations, weights and biases, and a lot of other libraries and frameworks. But yeah. So there's a lot of these integrations, as I mentioned, and Ray is really just a tool you can use to scale your NumPy, Pandas, TensorFlow, PyTorch code, and much more. And there's always been integrations being built. So this diagram is, let's say, 6 months old, maybe. And since then, there's been a lot of third-party libraries added to the Ray ecosystem, like LightGBM and Flammel yesterday, which is an AutoML framework by Microsoft. So to give everyone an idea of kind of where Ray fits in to programming life, so Ray is relatively similar to Dask, PySpark, Celery, Erlang, Akka, and more. So I just saw the question, does Ray work for arbitrary workloads using stuff like FFmpeg and Tesseract? I'd actually have to check because I haven't actually used FFmpeg with Ray specifically. But if you write down that question, or I write down, I'll save it to my desktop or whatever right now, and I can actually answer it on the Meetup channel after this talk, or in the comments of the YouTube video. More than happy to do that. So going back to Ray, Ray is really not a replacement for Kubernetes. Ray can run on top of Kubernetes, AWS, your laptop. And the main advantage of Ray is that you can run Ray anywhere. And there's always been, improvements to Ray. So Ray started a couple of years ago. Oh, I will just, okay.
Do you want me to read that one now? You got it?
Yeah, sure, you can read it.
What's easier for you? Can Ray be used to scale code across multiple cores of a single node, or is it just for multiple nodes?
So it can be used to scale across multiple cores of a single node, as well as multiple nodes. So the generality of Ray behind the scenes makes it really easy to scale between like a single node as well as multiple nodes. I do think I primarily have used it for scikit-learn, for example, for scaling across a single node across all my cores. But of course, you can distribute anything using Ray. And that's one of the beauties of Ray. It makes it easy to not only parallelize a workload across your local computer or your node, but also across a cluster, i.e. multiple nodes. So Ray has really gone relatively popular, even though it just started a couple of years ago. And there's been a lot of use cases, not just in production, but researchers have used it to startups, to hobbyists using Ray. This, of course, is being openly developed on GitHub, and there's been a lot of active contributors. So right now, it's growing in popularity, and contributions are typically going up. And so since distributed computing is really not a new thing, you might be wondering, like, why build a new distributed system as they've been around since the dawn of time? And Ray is Python 3. So in the 1980s, we had high performance computing running at supercomputers as well as today. In the 1990s, we had large scale web serving. And in the 2000s, we've had systems like MapReduce and Hadoop. And then more recently, we're having the rise of deep learning with tools like TensorFlow and PyTorch and much, much more. And what has changed these days is that these are really no longer isolated workloads. Before, you might be web serving all your traffic visiting a web page, and that would be really a standalone application. Molecular dynamics would be a standalone application, and these standalone applications often have specialized tools for them. But what we're having now is a bit different. We're starting to see a lot of these isolated workloads no longer be isolated. And so there really needs to be a general purpose system for supporting all these workloads. And so for an example of this, for reinforcement learning, for example, that really combines deep learning and training models with high performance computation and simulations. And then for online learning, you often have applications that interact with microservices and much, much more. And so really that's kind of the context for why Ray exists. And we can get to positives and negatives with this as well as comparisons later. The idea here is that Ray is trying to make it so you don't necessarily have isolated workloads anymore, or you don't need to have them. So I'll start by briefly going over the Ray API, and then we can get to questions. I'm trying to be very mindful of everyone's time here. And the Ray API is relatively simple. You just take functions and classes and translate those to distributed settings. So right here, we have two regular Python functions, and one reads a file and returns an array, and the other adds two things together. So you can take the Python functions and add a decorator on top, specifically the Ray remote decorator. And as a reminder, for those of you who don't know, decorators are a way to dynamically alter the functionality of your functions. There's a really great video by Corey Schaefer if you want to learn about them, or someone else to give a lightning talk at the next meetup. That'd be wonderful. Questions?
Yep, I was holding off. You said you were going to hold for a second. The first one is, no, that's all right. Just want to make sure when is a good time to ask them. When would you use Ray for distributed computing rather than PySpark?
So the best answer to that question is the simplest. If you find that you're happy with PySpark and you don't have workloads that are issues on PySpark, then don't change, right? Don't fix anything that's not broken. The more complicated answer to that question is I can give you a reference because that's a rather involved question, but I get that question enough, so I actually prepare an answer. So, all things have, positives and negatives. One issue and one reason people sometimes use Ray is that setting up Spark on a cluster and dealing with setups and dependencies for Java can often be not nice, is the best way to say it. And so Ray makes it really easy and a lot less configuration to run things on a cluster. There's a lot of other reasons the APIs are different. So here's just a quick comparison. I'd say Spark is a bit more coarse-grained, so it's a higher level API. And you can do a lot more like SQL-like abstractions, at least typically, before Ray had Spark integrations and vice versa. And Spark is more like functional, whereas Ray, I'd argue, uses an actor model, and it's more fine-grained, at least for the Ray core API. And if you have questions, we can go into the weeds with this. But essentially, Spark is, traditionally speaking at least, data processing and transformation. It's really great for data shuffling. And Ray, on the other hand, traditionally speaking, the original use case of Ray was reinforcement learning. So it's fantastic for really compute-heavy workloads. It's also becoming, surprisingly, really great for certain machine learning models in production, which is a whole other topic entirely. But if you want a comparison for that, I can actually share a comparison. There's a video by Jonathan, what's his name? Dino, hopefully I said that correctly. And he goes over like how it compares, step by step and, many code examples and so on and so forth. Okay, so the next question is, do all the nodes in the network need to be identical to use Ray? No, they do not. And that's partially why a lot of people like Ray. They can work with multiple different types of nodes, different types of compute resources, and much more.
Do you want us to hold off questions a little bit? Just let them come into a little bit later. Or do you want to interrupt you to keep it interesting? Which is easier? Better flow?
I don't mind either way, honestly.
All right. I'll see how the flow works, and I'll probably hold on, ask as we go, but I might hold it a little bit.
Yeah, it's perfectly good because I want to make sure everyone's questions get answered in a reasonable time setting, because these are fantastic questions. So we're going back to these two functions here, and Ray is really relatively simple. As mentioned earlier, you can take Python functions and add the remote decorator on top, and decorators really just alter the functionality of your functions. And when you want to call one of these functions, you add the remote keyword. It starts a task which can run async in your machine or cluster and returns a future. As a reminder, a future is the eventual result of an async operation. And because it immediately returns a future, this is really important. You can submit a second copy of the task before the first one finishes, and that can execute in parallel. And the idea is that futures enable parallelism. So you can also submit tasks that depend on previous tasks and so on and so forth. And actually get the values associated with these tasks, you can use ray.get. And while this is great and all, when you're programming, you use functions and classes. And so Ray can turn classes into actors. And if you're curious about actors, you can look up the actor model, which is kind of just how Ray runs behind the scenes. So right here, we have a Python counter class. And it's really just a simple class that's a single method for incrementing a counter. If you create an instance of the counter object, you'll create a service running the cluster that has a copy of that object. And you can call these methods on that object to submit tasks to those services. Those would return futures, and you can use ray.get to retrieve those values. So actors are a stateful service. So unlike the function part, which is stateless. So in Ray, we have tasks and actors. Actors are stateful and tasks are stateless. And all that really means, if you don't know stateful and stateless and all that, is stateful means you can have a mutable state, which lives inside the actor. So you can modify things a little bit. You can store data and so on.
What if I'm using subprocess? Will Ray pick that up as well?
Will I answer questions about that? I can hold off on that one to the end.
Okay, great.
Or just give resources to make sure we get through on time. So it's important to note that you can also specify resource requirements for actors and their tasks. So someone asked a question about, can you use multiple different types of resources together? You can in the same node and vice versa. So you can use GPUs, TPUs, more memory, and you can also specify what you want as well. And this is obviously not easy to develop behind the scenes. So Ray core is actually really interesting in case you want to go through the source code. So it's also important to mention, and I mentioned this like beginning of the talk. So Ray is an API for developing distributed applications and libraries on top of that. And while oftentimes we develop things in our laptop, Ray also has a cluster launching tools. So this makes it easier to launch clusters on AWS, GCP, Azure, Kubernetes, and much more. And one of the most important things, whether you use Ray or literally any distributed application, is finding a way to view it, debug it, and much more, because distributed applications are not traditionally the nicest things to debug at all. So Ray has a dashboard. And part of the reason why people have issues with clusters, and this goes, again, for every distributed framework, is that it can be real pain to debug across hundreds of clusters, look at log files, and then kind of look through them and see what's kind of important. So Ray is this kind of a dashboard to give you a single view to see what's important. And the point is, it makes it easier to understand what's happening in the Ray cluster easier. So you can trace and see how much memory is being used and much more. So part of the reason for having dashboards to see, are you using too much memory? Are you not using all your cores? Is it behaving the way you think it's behaving? Because it might necessarily do what you're thinking it's doing. So this goes for all distributed applications. I really recommend to go through them. In summary, Ray is really just a general purpose framework, which has a lot of integrations on top of it. In fact, a lot of users that use Ray, they're not actually, dealing with Ray core, which is the code I showed you today. They're oftentimes just running libraries on top of Ray, because a lot of the Ray stuff is abstracted away. Integrates well with libraries like PyTorch, TensorFlow, scikit-learn, and a lot more. And the idea of Ray is really just to have people think about application logic, not really servers, cluster sizes, instance types, and really just write application logic and scale up and down as needed. And the eventual goal here is to make distributed applications as easy as possible. By essentially just adding decorators, you can effectively distribute things across a cluster, and much more. So I'll leave this, end of this talk before I get to more questions with just a general ecosystem view. And so at the bottom, of course, is, Ray core, and that's kind of what little code we went over today. And using those like simple primitives, people have built a lot of things on top of it for, hyperparameter tuning, reinforcement learning, serving these into production, data processing, as well as a newer feature, but people also are doing data processing on top of Ray. So let's look at the questions, and I'll get to as many as we possibly can. And if for some reason I don't have an answer, I'll be sure to get back to you or whatnot. Okay. So one question is using Ray instance PySpark. I think that's been answered. Is it compatible with DPC++? I can actually ask that on the Slack channel just to see. More questions.
We have a couple in the Q&A part.
Sure. So one of the questions is, you can ask if you like.
No. I just, sometimes it's easier for you to, I think, just to go right straight on.
Sure. So how much work needs to be sent to the node so the overhead of Ray is a small percent of the total runtime? In other words, what's the time to send and receive a minimum amount of data from a remote node using Ray? So what's the time to send and receive a minimum amount of data from remote node when using Ray? So I haven't ballparked this as far as Ray 1.6. So I'd actually need to get back to you to get, an accurate number or see if, something like that. Because we just had a release 2 days ago, last week. And I haven't checked since like 1.3. So, and then when using subprocesses, will Ray pick those subprocesses up as well? It depends on what you're doing, of course. But for example, Ray has integrations with most libraries. So if Ray's integrated that library, Ray will pick that up as well. Some libraries it's not integrated fully yet with, so it's probably not. Yeah. And then this anonymous attendee question, I will actually get back to the anonymous attendee and post it in Baypiggies, like either YouTube video or whatnot, to make sure it gets answered. More questions? I can tell you some of the common questions I get. And feel free to interrupt me as much as you like, because, okay, some more questions. For the anonymous attendee, I'll get back to you about like different versions, how much work it takes to send something to remote node. I want to be as accurate as possible without speaking good or bad about any of these projects. Will work for pipeline with Kubeflow. So it should work for Kubeflow these days. That's something that's been active development within Ray. So yeah, Kubeflow should be fine. More questions? Oh yeah. So Alec is using Ray plus Kubeflow at his company. So Alec, out of curiosity, how is it working for you? Like, what are your pain points, out of curiosity? Oh yeah, let me let you speak. Alec?
Hey there. Yeah, so we are using Ray and Kubeflow. Basically, we built an in-house, or on top of Kubeflow, we built some functionality to do model tuning, hyperparameter tuning. And so we're using that component of Ray to automate the whole side of, we just want people to train models and not have to sit there tuning every little knob, just have the server do that for us. So it's working great.
What are any pain points recently? I'm just out of curiosity.
I didn't do that implementation myself, so I'm not totally sure.
Okay. So like one thing I always hear is it depends on the version of Ray. So I'm always curious to see like when people's pain points either go away or come back up or whatnot.
Yeah, I can't tell you offhand.
Okay. Thank you. Will it support Arglo workflow? For that question, I would ask on the chat. There's a Ray Slack channel. I can send it to you if you like. More questions? I know one thing to mention about Ray is it's like a massive ecosystem, and there's so many use cases, from like reinforcement learning, specific learning algorithms within reinforcement learning, offline learning, multi-agent learning, essentially reinforcement learning. And then it goes to Python applications. So the one thing about Ray is no one knows everything about Ray, as far as like all the integrations and so on and so forth. So the next question is from an anonymous attendee about what Anyscale sells. So I'm not here to market Anyscale as a product, and just Ray as a company. But if you're really interested and you want to see what Anyscale sells, it's basically a managed version of Ray, and it's basically the best way to run Ray. So that is what they sell for the product side. If you're curious, and I don't want to do a sales pitch here, you can press a demo, you can watch a demo, and so on. It's the managed version, basically. It's similar to what you see with Airflow and Astronomer and so on.
I just wanted to add a note about the, we take advantage of this rich open source community, and I totally appreciate that there are some companies who make a service out of it because they're complicated and hard. And getting some additional support, especially when you're wiring a jillion services together, it's hard to hire a team, depending on the size of your company or group, to somebody who can be an expert in everything. And even as you were pointing out, Ray is complicated. And then if that's only part of your business objective, hiring somebody who's just a Ray expert to support Ray when you may have a million other things to do. So there's a lot of companies that, that are not Python based open source tools, but have an open source component. Like you mentioned one, and then, Elastic has an open source component, and then you can use the Elastic Elk Stack service for, other kinds of things for managed services. And there's things for MongoDB just to add on to. But anyway, because I support what you're talking about in the open source tool. And then there's ways to blend that use of open source and also getting some help if you, don't have a team big enough to support all the widgets that, under the hood.
And for a lot of these companies, they're really making the best way to run the open source software, or they're, offering support, or they're consulting. Like there's a lot of different ways a lot of these companies make money based on their open source software. Yeah, and like you said, more questions. And if you have questions that you're curious about, feel free to reach out. One question from Prakash, hopefully I said that correctly. If not, sorry. Can you support quantum ML? At this moment, I don't think so. I haven't heard of integrations with quantum ML yet, but I could be surprised. There's always someone in the open source community working on some integration for Ray, or they're working with Ray to support something. It's a massive community. We're up to 500 and something contributors just in the open source side. Yeah. So a question. So as far as tutorials, playground tutorials to get started with Ray, someone asked me, so like anything, we're all biased about the best ways to learn something, the best ways to do something. I am extremely biased. So I wrote a tutorial about like getting started with Ray a week ago. So here's my recommendation. I do like puppies, so that's partially blinding my answer. But I just answered the question with this tutorial on the screen. So it goes over kind of what I went over really quickly about you have normal functions, what the Ray commands do. So like what Ray init does, starts processes, what Ray remote does, and then what remote command does, what a future is, and then Ray get returning values, and then as well as like using the dashboard, seeing the metrics, CPU, et cetera, and then distributed computing trade-offs, like do you actually need to scale? Are you using too much RAM? Are you being efficient? Are you trying to transfer data when you're using actors or tasks instead of actors? Like just a lot of little things, as well as like how to parallelize your workflow. Because oftentimes some code is just harder to parallelize. It's more serial in nature. So my recommendation. More questions. So let me just see. Open questions. So for Anyscale, do they have their own servers, or they use cloud providers like AWS? So Ray can run on any cloud provider, at least for the open source side. If you're curious about Anyscale and what goes on behind the scenes, I recommend you request a demo, see what's going on, because that's a company part of the talk, not the open source part of the talk. I'm not trying to sell anyone anything today, hopefully. More questions?
Hey, Michael, this is Jeff. I have a question for you. So I was playing with Ray a little bit, and I have like a cluster at home of like 3 nodes, and they're different sizes. And I was playing around with placement groups, and it was kind of hard to see why it kind of made certain decisions. Is there like some more documentation about that somewhere, or some place that would be the best place to ask?
Placement group specifically documentation. So the best place, and this is somewhere that most people ask questions, because Ray is a very, it's simple to use, but as far as like placement groups for, let's say, Ray tune, placement groups, how you arrange your computation, I would ask in the Ray Slack. So I can give you a Ray Slack invite, and for specifically placement groups, I would go under the channel. I would go under the channel tune, and you can ask questions about like, why are these placement groups, this way? Should I do a different way, and so on. So
Cool, thanks.
So how does Ray compare to term? I actually am not super familiar with term, so I can figure that for you. So it depends on, Prakash asked about GPUs from NVIDIA, AMD. So I've seen it work on GPUs of all types. I haven't, going back to like specific hardware, GPU wise, most people have gone by with multiple different types of GPUs. The one area where I think Ray is still like working on is Windows support. So our Windows support is not as developed as support for like Mac and Linux, for example, and M1 support on Macs. So those are areas of like work. GPU wise, Ray is running pretty well on different types of GPUs from different companies. More questions? Okay. So someone asked about how Ray compares to. Crash asked, does it not still not support ONNX? That is a question for Slack. And I'll get back to you about these questions. Ray is a massive, massive project. More questions? So, more questions. So that's it for the questions that I see that I haven't answered, or at least said I get back to people. Does anyone have questions about Ray comparisons? One more. Okay, so how many lines of code are in Ray and what language is it written in? So for these types of questions, it's really easy just to go to GitHub and see like how many lines of code are written, because this is open source. So you can see the contributions, you can see the rough breakdown of what languages it's written in. So for example, for Ray, a lot of it is C++ and Python. There are Java APIs. There's also a C++ experimental API as well. So I go through, want to count lines, you can count lines. But the one thing about Ray is Ray core is relatively simple to use, but there's a lot of different integrations. It's like going Airflow and looking at all the different providers for Airflow, for example. There's a lot of wonderful integrations with Ray. Anything from data processing, model serving, and much, much more.
Well, thanks a lot. That was
Thank you.
really great.
Thanks, and thanks for all the anonymous questions. And if you want to reach out to me about specific questions, feel free, and I'll be happy to answer them. I'll happy to get back to people. I can do like a Q&A. If you have questions, don't be shy. You can also go to the Ray Slack, and people are there that are experts in individual areas. Like if you're curious about a specific algorithm for reinforcement learning, you can go to the RLib Slack and ask. If you're curious about GPU support or specific GPU support, always go into the RLib Slack. That's typically where people have questions. Ray core, et cetera, et cetera. Okay.
Cool. Thanks a lot. And great talk. And thanks, Amish, for your talk on iterators. Does anyone have anything else before we go?
Just great talks, everybody. We really appreciate them. And thank you for volunteering to talk. And thank you for everybody who joined us this evening.
Yes, thanks to all the participants as well. And for asking all the questions.
Thank you.
Keeps it interesting. Okay, well, everyone have a great rest of your evening.
you.